These slides describe the kinetic theory of gases and the subsequent derivation of the ideal gas law. And first part of this slides would be key assumptions made in this theory, and this will be followed by simple mathematical steps, and each individual step follows Newtonian mechanics and algebra. However, things could become a bit more challenging as we move to the next section. So you want to pay really keen attention to these slides that are following here. So what we mean by kinetic theory of gases is we're building a model with specific assumptions as to the structure of the gases, and then use these assumptions to build mathematical relationships between different parts or properties of gases. The first assumption that we would make is that all gases consist of a very large number of very small particles. What do we mean by this? We say that a large number, meaning numbers on the order of 10 to the 5, 10 to the 10, etc. For example, Avogadro's number is 10 to the power 23 times 6. Therefore, we are dealing with gas samples under normal conditions that have excessively large number of molecules or atoms in them. We also will assume that the particles are so small that the net volume of the particles themselves is much less than the container volume. So if we say n is the number of particles, v sub I is the volume of the ith particle, then we simply saying if I were to sum all the volumes v1, v2, v3, v4, then that is equal to 0. And now v1, v2, v3, v4 are the volumes of individual particles. Of course, in a pure sample, these individual volumes are equal, but that is also equal to 0. So summation of 0 gives you sum of 0. And so this is an important assumption for ideal gases, that their volume be negligible. In real gases, however, the volumes are not really negligible. If you were to make precise measurements, we need to take into account of the finite volumes of gas particles in real gases. We'll see that in several lectures later. For now, we will assume that particles are very, very small to begin with. We also assume the particles do not attract or repel each other, meaning that each individual particle does not experience any force of attraction or force of repulsion from another particle that in the gas sample. Now, this assumption is also true only for ideal gases. In real gases, however, there's a weak interactions between particles, and that is a source for deviations from the ideal gas law, which again we will discuss under Van der Waals equation. For now, we will say particles do not attract or repel each other. So interparticle forces are 0. We also will assume that particles never come to rest. They just keep moving and moving and moving. And so they are in constant motion. However, when they're moving, of course they move in straight lines until they collide, either with another particle or with the wall. And so they travel in straight lines because there is no other force acting on them, according to the Newton's laws of motion. And only when they collide, they are likely to change their direction. And these collisions with other particles and also with that of the container wall needs to be elastic, perfectly elastic. This is what we will assume. In other words, the momentum is conserved as the collisions occur. And so we will use this as a key part of Newtonian mechanics. So to illustrate, in the bottom, you have a gas container, and the red dots are the particles, and the arrows depicting that they are moving in different directions. Note how the arrows are pointing in various directions randomly. So the gas particles are randomly moving within this container that is indicated by the blue lines. Now we will assume that the gas container has a rectangular cross-section of length L, right, and area of cross-section A. And our particle is moving along the x-axis. So this is an important assumption we make, that is, the particle moving along the x-axis. We can question this assumption later on and see what changes we need to make, or if no changes are to be made in our derivation. So the area of cross-section of the container is A. We'll assume that it is a rectangular box, and the x-axis length is L on that box, and our red dot is moving parallel to the x-axis, and therefore its momentum velocity are defined with respect to this axis. In the next slides, we have other properties to pin down. We will say that let m, lowercase, be the mass of each gas particle. And so we are assuming that the particle has no volume. But again, on the other hand, we are assuming it has finite mass. Okay, this is an important thing to keep in mind. So it's sort of an approximation. If you really think about it, there is a mass, how can the volume be zero? Of course, it's not going to be zero. All we're saying is the volume of the gas particle is so small with respect to the container volume, it is practically negligible. And v sub I be the velocity of the particle along the x-coordinate. So this is an important part of our workup. So the particle is moving along the x-axis with a velocity v. For the ith particle, we denote this as v sub I. L is the length of the box along the x-coordinate, and our particle is somewhere along on that length. It need not to be the beginning or end of the x-coordinate. It is somewhere randomly chosen to be somewhere in the middle. Okay, and N capital is the total number of particles in the container, as we have done before. Now, we will also assume that particles are traveling parallel to the x-coordinate. And this is not, again, essential, but it has an impact that we will discuss later on. So imagine that you have n number of particles of mass m, and they're moving along the x-coordinate with a velocity v sub I in a container of length L. Right? So these are the initial values and assumptions we make, and we move from here onwards. Our strategy is very, very simple. We're going to use classical mechanics. No quantum mechanics required in order to do these calculations. And we use the classical definition, pressure equals to force divided by area. So if a gas is exerting certain pressure, implies that the gas is applying certain force on a particular area that we are interested in. So we're going to calculate the force, and which we're going to do by, again, applying classical mechanics. Force equals to the rate of change of momentum. So if we can calculate the rate of change of momentum, we can calculate the force. We know the area cross-section of the container. We can calculate the pressure. So the strategy of calculating pressure boils down to two important things. That is determining the force and determining the area cross-section. Force, in turn, can be obtained from calculating the rate of change of momentum when the gas particles collide with the wall surface, which we're going to do in the following manner. So here is the approach we're going to take. And I've broken down the approach into individual steps where we can understand each individual step much more readily. So we will first compute change in momentum when just one particle hits the wall. The wall is now placed perpendicular to the x-axis with the area cross-section A, as we defined on the previous slide. Then we're going to calculate the number of collisions made by this particle in 1 second. So as the particle bounces back and forth, so that is, when it hits the wall, it is moving parallel to the x-axis, and the wall is perpendicular to the x-axis. So when it is bounces back, it is going to travel again in parallel to the x-axis, but in the opposite direction. And so now it's going to collide with the opposite wall, and the same thing happens. It will be bounced back to the forward wall. So the particle is now making excursions between the left wall and the right wall parallel to the x-axis. This is the kind of thing I want you to imagine happening. Now, at this point, as the particle is bouncing back and forth between the two walls, which are kept perpendicular to the x-axis, we're going to calculate the rate of change of momentum. It means the change in momentum of the particle each time it collides in 1 second. Okay, that is the rate of change. We can calculate the momentum for one collision, then we count how many collisions are taking place in 1 second. That gives us a rate of change because there's no change in momentum per second. Then from the rate of change of momentum, we can calculate the force exerted by that one particle using the above equation that we described from Newtonian mechanics. Since we know then the force exerted by one particle, we can calculate the pressure exerted by one particle because we know the area of cross-section of the vessel. So if once we figured out the pressure exerted by one particle, we can now readily calculate force exerted by all particles. Right? You can obtain this in a couple of different ways, but one of them is much better accurate way than the others. We will discuss that on the next slide. So if we once you know the force exerted by all particles, we can now calculate the total pressure of the gas on one wall. If we know the total pressure of the gas on one wall, we can deduce the pressure on any wall from that onwards. It's all logically and sequentially described. So let's get to the work and figure out the math for each of these steps. So on the next, this slide, we have now translation of the steps we described on the previous slide in terms of mathematical details. So let's consider first one particle. It's making just one collision with the wall, kept perpendicular to the x-axis, and the wall area cross-section is A. Let's keep these in mind. So the momentum of the particle before it collides with the wall is simply equal to its mass multiplied by its velocity. So mv. Momentum of the particle after the collision with the wall, that is, as it bounces back, is going to move exactly parallel to the x-axis but in the opposite direction. Since the direction of the particle is changing, we then write the momentum of the particle is equal to m times minus v. So it's very important to remember that the direction of the velocity is changing as the particle bounces back. So if mv is the momentum prior to the collision, minus mv will be the momentum after the collision. So now we can compute change in the momentum of the particle due to just one collision with this particular wall. That's equal to minus mv minus mv. What does this mean? Final momentum, which is minus mv, minus initial momentum, which is plus mv. So minus mv minus initial momentum, which is mv. Therefore, the total is minus 2mv. This is important. Very often, the mistake is made as this to be equal to 0. That is, we often forget to put the negative sign on the first term. Now let's keep this discussion going. So now we have a box of length L, area cross section A, and our particle is bouncing back and forth within this, right? The length of the box along this x-axis is L. So when it travels to the right, it hits on the right wall and bounces back, travels to the entire length of the wall of the box, and then collides with the wall on the left side, and then bounces back from the left side, travels to the right, etc. So it is making round trips as it goes back and forth. Since each collision is perfectly elastic, this kind of motion will continue forever, right? There's no loss in the energy of the particle as the velocity, as the collisions are perfectly elastic. Now, keep this in mind, and we now can calculate the number of collisions made by the particle at one of the walls, that is the wall on the right-hand side, by the particle in 1 second. So now we ask, how many collisions does this particle make on that wall that you kept on the right side? And that's, of course, depends on how many round trips it's going to make. The length of the box along the x-axis is L. Therefore, the round trip length is simply equal to 2L. So distance traveled by the particle in 1 second is equal to v meters, because that's its velocity. It's going to travel v meters in 1 second. However, the distance of one round trip is 2 times L meters, because L is the length, so it has to travel the entire length and come back to its original position, as shown by the 3 arrows above. So if you sum the distance of all the 3 arrows above, that will be equal to 2L. So in 1 second, the particle is traveling v meters, and we have a round trip distance of 2L meters. Therefore, how many collisions does the particle make in 1 second on the right wall? You simply divide v meters with 2L, right? So again, let's look at this very carefully. V is the number of meters the particle travels. 2L is the round trip length. So if I divide v with 2L, it should give me the number of round trips the particle is making in 1 second. In each of the round trips, the particle collides only once on the right-hand side wall and only once on the left-hand side wall. We do not care about the left-hand side wall. We only care about the right-hand side wall, because we're going to measure the pressure using that one particular wall. Okay? So in 1 second, it is making v over 2L round trips, and however, for each of the collision, the change in momentum is minus 2 mv, as we derived above. So now we can calculate the rate of change of momentum, meaning the change in the momentum of this particle in 1 second along the x-axis. That is simply multiplied by the two quantities, change in momentum for one collision multiplied by the number of collisions made in 1 second with the wall on the right-hand side. So that's minus 2 mv, that's the change in momentum, or one collision. Multiply that by v over 2L, that is the number of collisions one particle is making on the wall. So the rate of change of momentum of one particle is equal to minus mv squared over L. So now we will ask, what is the force exerted by this collision of one particle at the wall? It's simply force exerted is equal to the rate of change of momentum from Newton's laws of motion. So we can now conclude then the force acting on the particle during the collision by the wall is minus mv squared over L. So that's the force we calculate from Newton's law. So remember, this is minus mv squared over L. That is, the force is acting on the particle exerted by the wall. As the particle collides, it's bounced back. So force acting on the particle will be exactly opposite. force acting on the wall is exactly opposite to the force acting on the particle. Therefore, the force exerted by the particle on the wall is now plus mv squared over L. So sign is changing here. So once we know the force, we can now calculate force per unit area, which is equal to pressure. So that equals to mv squared over L. And we multiply L with A in the denominator because per unit area. A is the area cross section of the wall placed perpendicular to the x-axis. So this is essentially the pressure. Now we can simplify the length of the box multiplied by the area cross section is equal to volume of the box. We assumed a rectangular box of area cross section A. So L times A is now equal to V, capital V. So that's the reason to replace LA with V. So now we have managed to calculate pressure exerted by one particle. So that's equal to m small v squared divided by capital V, the volume of the box. So since we know now the pressure due to one particle, we can simply calculate the pressure due to all particles. So we could do it in a couple of different ways, but simply multiplying this pressure we have by capital N, the total number of particles, will not give us the actual value. So we cannot do it by simply multiplying with the number of particles, and I would like you to think about why that is before we move on to the next slide.